Well, hello again. We're going to talk about fluids. And for our purposes, a fluid is a liquid or a gas. But to talk about a fluid, I need two concepts first. I need the idea of density and the idea of pressure. So first, density. Density, by definition, is mass over volume. We give it the symbol lowercase rho. The Greek letter rho is m over v. So this is very straightforward. So for example, the density of iron is 7.86 grams per cubic centimeter. That's often tabulated in grams per cubic centimeter. For calculations, need it in kilograms per cubic meter. So just to remind us to practice how we would convert that. So there's 100 centimeters in a meter. We'd have to cube that conversion. To go to kilograms, we'd need kilograms over 1,000 grams. And so this gives us a factor of 10 to the 6th over 10 to the 3rd. So we always get a factor of 1,000. So this is 7,860 kilograms per cubic meter. So that's the density of iron. Similarly, the density of water is 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. So that's the density. It's a property of a substance like that. If you have the density and want to know the mass, you go the other way. Of course, the mass is just the density times the volume. We will see that a lot. We'll use that today, and we'll use it in several other days as well. So that's density. We also need a concept called pressure to work with fluids. Now, pressure has more uses than just fluids, and to introduce the concept, I'm going to introduce it not using a fluid, but just for an object sitting on a table. So pressure, by definition, is force over area, or just P is F over A. Units for force are newtons, area is square meter. So, and a newton per square meter by definition is a Pascal. Although sometimes people just write newton per square meter. Pascal is expressed as PA. We especially use Pascal when we're talking about fluids. So suppose, for example, that I want to calculate the pressure due to a cube of iron sitting on a table. So this is iron, and it's sitting on some table, and it's 0.5 meters by 0.5 meters by 0.5 meters, and I want to know the pressure that this iron pushes down on the table. Well, the pressure is its force over area. Well, what force? The force down at the area of contact. So that's the area down here, and the force is just the weight of the iron. So the pressure will be the weight of the iron over the area where they're in contact there. So this will be the mass. Okay, so I need to know the mass. The mass, as I just said, is the density times the volume. So the mass is the density, 7,860 kilograms per cubic meter. That's just a property of iron. That's why. The volume of this cube is 0.5 meters cubed. So that mass of that big chunk of iron sitting there turns out to be, let's see, 982.5 kilograms. So a lot, around a ton. Tons of force, but still. So this is now 982.5 kilograms times 9.8 meters per second squared over 0.5 meters squared, and that is 38514 Pascal. That's the pressure, the force per square meter, the newtons per square meter that the weight of that iron would push down on that table. All right, so that's the two concepts I needed just to get started: density and pressure. So our first topic in actually talking about fluids is the variation of pressure with depth in a fluid. And for our fluid, we're going to use fresh water as an example. So this would be like depth in a lake. So suppose I have the surface of the lake here, and I want to know the pressure down below that surface. Here's a way we can derive that. I'm going to hypothetically think of some column of water of depth h and cross-sectional area A. And I'm going to balance the forces on that column of water. So that column of water has a weight, mg, that's the weight of all the water in that column. There's a force up on it due to the pressure of the water below pushing up. There's a force down on it that's due to the atmospheric pressure pushing down on it from above. So the force down is just the pressure at the top, I'm going to call that P0 times the area. The force up is the pressure down here, which I'm just going to call P times the area. Balancing all these forces gives me the force up, P times the area, is the force down, P naught times the area, plus the weight, mg. But I just saw that m was density times volume. So this gives me PA is P naught A plus density times volume times G. But the volume of this column of fluid is its height times its area. So this is PA, it's P naught A plus density times height times area times G. And now I have an area in every term, and it cancels, and I've got P is P naught plus rho G H. And there's my equation for pressure at depth. This says the pressure at depth H is the pressure at the top plus this rho GH. That's the pressure due to the weight of the water above it, or whatever liquid it happens to be. So, for example, what is pressure at 20 meters depth if P at the top, that was supposed to be a P and it looked like a rho, so I'm going to be careful. If P at the top is 1 atmosphere. Well, what do we mean by 1 atmosphere? 1 atmosphere is a standard unit. One standard atmosphere, by definition, is 1.013 times 10 to the 5th Pascal. So this is just plug in. We've got P is P naught plus rho GH. The P at the top is 1 atmosphere, 1.013 times 10 to the 5th Pascal. I can't just write it as an atmosphere because then my units will be mixed up over here. Density of water is 1,000 kilograms per cubic meter. G is 9.8 meters per second squared. H is the 20 meters. So P at the top is this 1.013 times 10 to the 5th Pascal. It's 1 atmosphere. Plus all of this stuff turns out to be 1.96 times 10 to the 5th Pascal. Or P, well that's not P at the top, that's P at that depth. P at depth H. This is P at the top. So P at depth is the sum of these two things is 2.97 times 10 to the 5th Pascal. Let's think about what this means physically. This says at this depth, at 20 meters down, the absolute pressure is this. But note what that means. This is the pressure due to the atmosphere at the top, and this is the pressure due to the depth of the water. Often, you only care about the pressure due to the water. you were already, before you jumped in the water, if that's why you care about this, if you jumped in the water, before you jumped in, you were already at 1 atmosphere. So this is just the pressure that you gained by going to that depth. So this is sometimes called the gauge pressure. So in this particular case, we're saying pressure at that depth is the atmospheric pressure plus the gauge pressure. Often we only care about how far the pressure is above or below an atmosphere because we live in 1 atmosphere. When you inflate your tire, if your tire goes flat, even when it's flat, it still has atmospheric pressure in it. You didn't hook a vacuum pump to it and evacuate it. It just went down to 1 atmosphere. So what we sometimes care about is just pressure above or below atmosphere. Sometimes we care about absolute pressure. So this equation over here tells me absolute pressure is atmospheric pressure plus gauge pressure. So just to get this in your notes, to make sure we understand this, P absolute pressure is pressure relative to vacuum. That was supposed to be the word relative. Couldn't possibly read that. Whereas P gauge pressure is pressure relative to atmosphere. And which one you need just depends on what you're doing. Often in scientific experiments, you need to know absolute pressure. Often in everyday life, you need to know gauge pressure. And to relate the two, you add atmospheric pressure plus gauge pressure gives you absolute. All right. So let me do another example, and then I'm going to talk about pressure measurement, and then we'll call it a day. So in the example that I just did, let's see. Well, no, let me do another one. Example 2. At what depth is gauge pressure five atmospheres? Well, P absolute is P atmosphere plus P gauge. That P gauge is just rho GH. So H is P gauge over rho G. So that's 5 atmospheres times 1.013 times 10 to the 5th Pascal per atmosphere to make our units work out. Over 1,000 kilograms per cubic meter times 9.8 meters per second squared. That gives me 51.7 meters. So that says if you go down 52 meters, the gauge pressure is 5 atmospheres. So that's part A. Part B for this, what good does it do to know that? Well, suppose you're diving and you're wearing some scuba gear, and this is the glass visor on your scuba gear. And suppose that visor is, let's see, 5 centimeters by 10 centimeters. And you want to know what's the force on that visor. Well, force is pressure times area, because pressure is force over area. The pressure that matters here is the gauge pressure, pressure above or below atmosphere, because you presumably have 1 atmosphere inside the visor. So this force will just be the gauge pressure, 5 atmospheres, times 1.013 times 10 to the 5th Pascal per atmosphere, to make the units work, times the area, which is 0.05 meters times 0.1 meter. And that will give me the force on that visor. That turns out to be 2533 newtons. So quite a lot of force. That's really a really big force. So one more topic, pressure measurement, the idea of a barometer. Now there are other ways to measure pressure than a barometer, but than a historic barometer, a historic mercury barometer I'm talking about. But there are units that depend on a historic understanding of the mercury barometer. Suppose I have a little pool of mercury here, and I have a tube containing mercury, so this is mercury, and I take that tube, it's open at the top here, and I turn it over and quickly put the closed end inside this pool of mercury. I'll end up with something like this. I'll have the tube of mercury, and all of the mercury will not run out and pour out. The mercury will just settle down a little bit and leave vacuum at the top. This is like if you've ever been washing dishes in a pool of dishwater and you pull a glass of water up and the water stays in the glass until you pull it all the way out of the water. The atmospheric pressure holds pushing down on the water, holds the water in the glass. So the atmosphere, you've got atmosphere pushing here, you've got vacuum here. And this is a barometer, a mercury barometer. So what we have now is the pressure inside here. Let's look. We've got the pressure at this depth, P there, is P at the top, plus rho GH. But P at this depth is the same as P out here. So P out there is atmospheric pressure on the day you're trying to measure it. P at the top is 0 because of how you made the barometer. And so atmospheric pressure is just rho GH with this barometer. You make these using rho to be rho of mercury because mercury is a very dense liquid. So let's calculate what H would be for, if we want to make one of these, for one standard atmosphere. So H would be P atmosphere over rho G. This is 1.013 times 10 to the 5th Pascal. The density of mercury is 13,600 kilograms per cubic meter. Mercury is so dense that you can float steel in it. Over 9.8 meters per second squared. And this turns out to be 0.760 meters, or 760 millimeters. Millimeters of what? 760 millimeters of mercury, which you've probably, some of you in other classes have heard of. That in fact, one standard atmosphere is 760 millimeters of mercury. That's where that comes from. And so a standard atmosphere is the pressure that can hold up a column of mercury that is 760 millimeters high. A column of mercury 1 millimeter high exerts a pressure called a torr. So this would also be 760 torr if you've run into that unit as well. All right, well that's a lot. You can practice that as always in your homework.